Hello, my name is Patrick, one of the TA of PHYS3041. So this is the first exercise class. For today's exercise class, we will mainly focus on the application of, for example, Biot-Savart law, and also how to obtain the electric field, and of course the magnetic field, so that you know how to do your homework. I assume that you already have a look on the exercise class problem set. So let's start to discuss the solution here. So this is the first question. This is actually from Griffiths. So this problem required us to find the electric field at a distance z above one end of a straight line segment of length L, and it carries a uniform line charge lambda. So again, for every problem, every physical problem, the first thing you need to do is to formulate correctly of your problem, and then of course put your problem in some appropriate coordinate. For example, we set the vertical axis here is z-axis, and the horizontal axis here is the x-axis. So it is clear that this variable r squared equals to z squared plus x squared. And then we can directly apply the equation we know to obtain the electric field. Note that the electric field is a vector, so it is not that straightforward if you do the integration directly. So the best thing we need to do, the best thing for us to do now is to decompose it into two directions, and of course on z direction and also x direction. So we split it into two equations, and from the configuration here, you can see that it is obvious that the z direction of electric field is the whole electric field times the cosine theta. And of course, the x direction here is the same thing with sine theta. Don't forget a minus sign here. This is because the positive direction of x is defined to pointing to the right, where the electric field on x direction is pointing to the left. That's why we have a negative sign here. So with some change of variables, you can substitute or change the cosine theta and sine theta with the coordinate variables we know. So we can express the integration in this following form. And then so the last thing we need to do is just a straightforward calculation, some straightforward integration. So you may check, for example, Mathematica or any mathematics software, or even check the integration table to obtain the outcome here. So let me skip the mathematical detail and show you directly the result. So once you do the integration properly, you will obtain these two results. Again, they represent the Z direction of the electric field and also the X direction of the electric field. And then if you combine this into a vector form, then you've obtained the solution you want. So this is a basic process or routine how we obtain the electric field from a given charged source. So let me recap all the things again. So again, if you have a problem, draw down its configuration first. It helps you to visualize the problem, and then formulate the problem in appropriate coordinate. It will make life easier. And then you can apply this integration to obtain the electric field. And don't forget to decompose it in different directions. Otherwise, the integration could be very complicated. And then just some straightforward calculations, and then you will get this. Okay. So for the second question here, we prepared a problem also from Griffiths, is that asking us to obtain a electric field, a magnetic field at point P here, and the setup shown in this problem. Okay, so as this is not infinitely long problem, so you cannot directly apply some Ampere's law or some symmetric or some simpler way. So the only way to do this is to apply the Biot-Savart law directly. So now to deal with this complicated problem, we can first focus on another simpler problem. So as shown here, this is an example in Griffiths 5.6. So what it required us to find is again the magnetic field at a given distance for a circular loop. The radius, the distance, the angle here are all given. And also the static current I is carried by this circular loop. So to work out the magnetic field, we can directly apply the Biot-Savart law here. So I write down the Biot-Savart law here, and note that in this configuration, the length of various r or various r squared, and also the distance z are constant, and also the theta, of course. So you can factor out some questions outside the integration, and then what you will got integration of dl prime only, which represent an integration of a circular loop, and it is obvious that this integration will return you a 2 pi r here. So if you reduce all the things with the coordinate variables, then you can re-express your magnetic field in this following form. So why we need to obtain this result first? This is because for this question, you may consider it as a combination of a lot of this kind of circular loop. So, however, for each circular loop, you may consider its steady current now becomes NIDZ. I is the total current passing through the whole solenoid, and the N is a number of loop per unit length. So so N dz represents the number of loop passing through here, and then times the steady current, then you will obtain the whole circular, the steady current of the whole circular loop at this specific location. So in equation 12, I re-emphasize or I reformulate the same result we obtained before. Let me go back a slide here. So I basically copy this result, but with different notation. This is because the radius here is A from the problem with no. So now what we need to do is to integrate the whole solenoid dz here. So we need some more change of variables so that we can do the integration successfully. And since A can be expressed as A times cotangent theta, so if you find its derivatives, dz, then you will obtain this, A over sine square theta, don't forget the minus sign, d theta. And then you can also express this 1 over something term into sine function here. So if you substitute equation 13 and 14 into the original equation, say equation 15, then you will obtain a easy, straightforward integration here as shown at equation 16. And this is straightforward calculation, so obviously what you will get is equation 17. So this is the solution of this problem. Of course, based on what you've learned before, you can do some consistency check. For example, let us assume that this is a infinite long solenoid. Then it is okay here. So assume that this is an infinite long solenoid. Then you can expect that one of the theta 1, for example, theta 1 could be equals to 0, and theta 2 is equals to pi, right? If this is an infinite long and it goes through point P and so on, so one of the angles should be 0 and the other one should be pi. And then if you substitute the thing, the angle here, you will have a factor extra after factor 2 here. and then you will got mu naught I. So this is the result from if you work on an infinite long solenoid. So this is pretty much it. Thanks for watching this. Good luck on your assignment.